Hello, in this module we will introduce the sampling theory and will learn the sampling process. Today we will discuss the ideal sampling process, which is also called the instantaneous or the impulse train sampling process. The sampling is usually described in time domain, though it is possible to think of the sampling of any continuous signal. Sampling is a basic operation in digital signal processing and in digital communications. For example, in digital communications, the message that is transmitted, the information is usually in analog form, such as speech or music, but it is processed digitally, both in the transmitter and at the receiver. For the digital processing of the signal must first be converted to digital form, and therefore the first essential block in any digital communication system is A to D conversion, analog to digital conversion. An analog message signal is one which is continuous in time as well as continuous in amplitude. It must be converted to a signal which is discrete in time as well as discrete in amplitude, and such a signal is called a digital signal. So this analog to digital conversion essentially involves two steps. The first step is to convert the continuous time part to the discrete time part, to discretize the signal in time domain, and once it has been discretized in time domain, the second step is to discretize it in amplitude from continuous amplitude signal. So the first step is known as sampling, converting continuous time to discrete time, or discretize the signal on time axis, and then the second step, which is the discretization of the signal on amplitude axis, is called the quantization. In this module we shall discuss the sampling process, the first step. So consider a continuous time signal. Say m of t, and we want to discretize it in time, meaning that we want to obtain the signal samples at discrete instants of time, say some ts or 0 ts, 2 ts, 3 ts, and so on, and also for negative time instants minus ts, minus 2 ts, and so on. As we can see, the signal values at these time instants are given by these cross marks. So we want to obtain these sample points from the original signal, and how can that be obtained is the question we would like to answer in this module. More specifically, as you can see here, we want to obtain the samples at the time instants separated by ts. This ts is also called the sampling interval, and the sample values that we obtain are m of 0, m of ts, m of 2 ts, and so on. So how can we obtain such a representation of the original signal? So let us again consider the same message signal. M of t, we claim that when the signal is multiplied by a periodic impulse train with impulses separated by ts interval, 0 ts, 2 ts, 3 ts and so on, then the resultant signal would be the sampled version of the original signal. Let us represent this impulse train by delta subscript capital Ts of t. Our claim is that when these two signals are multiplied, we get the sampled version of the signal. So to see that, let us first represent the impulse train mathematically. This impulse train comprises impulses occurring at 0, that is delta t, impulse occurring at Ts, that is delta t minus Ts, the impulse occurring at 2 Ts, that is delta t minus 2 Ts, impulse occurring at t equal to minus Ts, that is delta t plus Ts and so on. So in general, we can write down the impulse train as delta t minus n Ts summed over all n from minus infinity to plus infinity. So this is the mathematical representation of the impulse train. Now let us assume that when mt and the impulse train are multiplied, we get another signal which is m delta t. So m delta t is equal to mt into the impulse train. So what do we get? So it is equal to mt into summation n from minus infinity to plus infinity delta t minus n Ts. Now mt doesn't depend on n, so it doesn't matter whether we write it outside the summation or inside it. So let us bring mt inside the summation and write summation n from minus infinity to plus infinity mt delta t minus n Ts, and here let us invoke a property of impulse function. So recall that if in general we have some signal xt multiplied by an impulse delta t minus t naught, then it is another signal x of t naught delta t minus t naught. So xt delta t minus t naught is same as xt naught delta t minus t naught. So using this property, we can write here that our signal m delta t is equal to summation over all n from minus infinity to infinity m n Ts delta t minus n Ts, and this is an important result. Let us box it. What does this signal represent? This signal, as we can see, it is the summation of impulse. It is an impulse train, summation of impulses scaled by m and Ts. So when n is equal to 0, scaled by m of 0, which is the signal value at m equal to 0. When Ts equal to, when n is equal to 1, it is m of Ts, which is the signal value at n equal t equal to Ts, and so on. So in effect, we get an impulse train. So we get a signal which is, let us first make the profile to clearly show it. So we get a signal which is an impulse train, and impulse is occurring at t equal to 0, t equal to Ts, t equal to 2 Ts and so on, minus Ts and so on, and we can see Ts, 2 Ts minus, sorry, this 0 is minus Ts, and we can see that the strength of the impulse here is, this is m of 0, this is m of Ts, this is m of 2ts, this is m of minus ts, and so on. So we see that we get an impulse train with the strength of the impulses equal to the message value at those instants. So let us make a note of it. So the signal m delta t represents an impulse train with impulses separated by ts, so ts, 2ts, and so on, and the strengths of the impulses given by the signal values m0, mts, m2ts. So signal values at instants where the impulses occur. These instants are called sampling instants, the interval ts between successive sample values is called the sampling interval. The reciprocal of the sampling interval 1 by ts is called the sampling frequency, and it is usually denoted by fs. So we have seen and we have shown that when a message signal is multiplied by a periodic impulse train, we get the sampled version of the signal. Now the question arises that if we represent a continuous time signal by selecting its value only at discrete time instants, wouldn't there be any loss of information? Can the samples of the signal represent the signal perfectly, or is it possible to perfectly reconstruct the signal from the signal samples? So these are the questions as we have put here. Can a signal be represented perfectly in terms of its samples, or equivalently can a signal be perfectly recovered from its samples? So the answer to these questions lie in what we call the sampling theorem. The sampling theorem and related aspects we shall discuss in a subsequent module. So that's all for this module. Thank you.